Okay, great. So this is the explainer about supervised versus unsupervised learning. I mentioned this in the Introduction to Machine Learning first explainer. We're just going to dive into more detail here. I've put supervised versus unsupervised learning, but what I really want to highlight, it isn't a competition. So the versus really shouldn't come in there. It should be supervised and supervised learning. But often it's classed as a sort of seen as either or. It really just depends on the class of problem or task that you're trying to achieve machine learning. So fundamentally, we're going to go through those two examples, give examples of the types of algorithms that you would look at, different classifications of supervised and unsupervised learning, so they're subsections. And then we're going to look at semi-supervised learning, which is a hybrid of the two, just really at a high level. And then finally, we're going to go on to reinforcement learning, which is a really nice area, which is learning how to control systems through experience. We'll get on to that. So let's do it. Okay, to highlight again, supervised versus unsupervised learning is often pitched. You'll see LinkedIn posts, which one's better, which one's not. It's not one's better than the other. They're just fundamentally different tasks. And you should be able to understand, given a challenge, what task, what type of learning algorithm that you need to use. So supervised learning, at a simple level, is really learning from labelled examples. This means I show you examples of inputs X, outputs Y, and then I want to learn a machine learning algorithm that mimics that process. We supervise it by giving it examples to learn the task at hand. Unsupervised learning is there's no labelled data, so it's just all inputs. And what we're trying to do is find patterns or similarities in that data to extract knowledge or information about that data set. In machine learning, these patterns are often called features, and you'll hear that used quite a lot. I personally think of machine learning as a pipeline of algorithms. So this is moving you from real raw data all the way through deployment and validation of your machine learning algorithm. And I would say that a lot of the time, both supervised and unsupervised algorithms are used in tandem in algorithms. So often unsupervised learning is used as an initial step to simplify the patterns in our data and make it easier, followed by a supervised learning task where we try and mimic examples of that data. Okay, so first we're going to deal with supervised learning around learning from examples. So don't worry about the maths here, but we'll try and put a bit of math notation in there so you start feeling comfortable with some of the maths terminology that you'll see when you see more machine learning. So what we say is we have a training set, and in maths we denote a set by these curly brackets. Just imagine it's a bucket, right? A bucket of examples in it. In this bucket of examples or set, we then have examples which are paired together. X's are the inputs, Y's are the outputs, and they're given a number each to identify them. So X0, Y0, X1, Y1, all the way up to Xn, Yn. So we have n samples in our data set. Now the task at hand really is to think, or a simple way of thinking is, right, we have a machine where we can feed in inputs and it can spit out outputs. And so we denote this output of the machine as f of x. This basically says it's a function of the input. Now what we want to try and do is we want to supervise this machine in when we give it a particular x input, the f of x is very close to the label that we want, or the output, or the, not necessarily a label, get into that, the output y that we've got paired in our data set. And we want this to be true over all of our training data, but we also want it to be true over data we haven't shown it at training. This is a concept of generalization, which we've touched on in the last explainer. Okay, so under supervised learning, there are broadly two classes, classification and regression. And what this really depends on, if I jump back to the previous slide, it all depends on what Y is. If it's a label, then we call this a classification task. If it's a number, temperature, for example, or price, for example, then we could see it as a regression task. They're both supervised learning algorithms, but different methods. Some can do both, but different methods are suitable for classification against regression problems. So it's not either or, it just depends on what data you have. You can also have more complicated methods, which are combinations of this, but we won't touch that in this explainer. So to give you an example of classification, example that I use a lot, if we have inputs of images of either cats or dogs, then the labelled outputs will be associated outputs with that picture. So here we've got cat, cat, dog. We feed these in the machine to the example, and then we want the machine to see an unseen picture, here a picture of a dog, and it's learnt by example that it has similar features to other examples of dogs, and it classifies that picture as a dog, hopefully. On the other hand, we have a regression task. So here we might have two sets of inputs, here from 0 to 100, just a made-up example, and then the data lives on these black dots. What we want to do is to generalize or learn to areas where we haven't yet seen data. So in this regression task, we've basically fitted a surface, a curve, to that data to try and recreate that data to give our best predictions to unseen data. So where we don't have the inputs, but to try and make good predictions. This is a typical regression algorithm, not the only way to do it. There are many, many, but curve fitting in this case is a classic example of regression. So here's a challenge for you. You can stop the video, but I would encourage you to go and find out about 5 supervised learning algorithms. I don't mean in detail, because that's what this course is about, is diving in the detail. But if you can get on ChatGPT, say, give me 5 supervised learning algorithms, do it. Google will give you the same. And just come back and, just having found 5 and distinguish. Now, if they give examples with it, think, is it a classification algorithm or is it a regression algorithm? So hopefully you've done that. And I'm going to give you 3 now. So I didn't do the full 5. I'll give you 3. The first one that you're going to see in this course, actually, after this video, is k-nearest neighbour. So it's like a more sophisticated version of lookup table. So what we have, so we're going to think about it for a classification problem, but I also cover the regression problem in the next explainer. So what we have is we have the space of possible inputs. So imagine this area represents different x values with 2 values, 2 coordinates. In each of these, the labels identify as green triangles or yellow squares. And this is the classification. So the shape and colour of the data point represents its label. Okay, so now we ask the question, well, we've got a new instance here. We want to know if we had this as an input, what would the output be in terms of label? And what k-nearest neighbour does, so in this case the k stands for is a number, in this case we're looking at 3, it will find the 3 nearest points. We'll discuss what near means, but in this simple case it just means measured distance. The 3 nearest points, and then we take a majority vote. So in this case we say the 3 nearest points to our new instance, 2 are green, 1 are yellow, and then, okay, so we will classify this point as green triangle rather than a yellow square. Nice simple algorithm. We'll dive into the details more, but an example of using labeled data to make predictions of unseen data. So in this case, it's a classification example and it's supervised learning. So I've touched on this. So in general, curve fitting could be seen as linear models, and you'd be like, well, linear models just are straight lines. We will cover in this course that actually linear models can be more complicated than straight lines, and we'll get on to why even fitting polynomials or more complicated functions can be seen as linear models as well. But essentially what you're doing here is you define a way of defining a curve. So this could be polynomials, it could be straight lines, it could be other types of functions that you put, and then you find the best fit, the least squared fit to the data. So you try and minimize the error between the data and the prediction. And so this gives you a predictive curve. Some people call it a response surface around making the predictions. In this case, supervised learning and a regression, because the output is a continuous variable. It's a number, right? And one of my favorites, a deep neural network. So deep neural networks are mimicked on the way we solve problems. Our brain is set up with neurons. I won't get into lots of detail in this course, but in the next course with Andy, he starts to touch on deep neural networks and more complicated models. What happens here is that the input, so I've gone back to the classic, is it a dog or is it a cat picture? What we have here is the picture goes in, the pixels form the inputs to the neural net. It's then passed through a series of weights onto hidden nodes through activation functions, we won't get into the detail, all the way through this network where it outputs a choice, a classification of problems. So here, if the second one they've identified, if the second one says 1, then essentially this is a dog classification. Maybe one of these is a cat or other animal, for example. I'm just saying, I don't know in this particular example. What then happens is the weightings of these, each of these components is then adjusted so that the behavior reconstructs the right label output given examples. So this is an example of a classification problem, and again, supervised learning because we're giving labeled data. Neural nets work for both classification and regression tasks, so it's not just a classification with neural nets, but nice example. You'll learn more about them in the wider AI in the Wild series. Okay, so unsupervised learning is different. We're trying to find patterns. And I said, oh, it's your best friend in highly parameterized models. What I mean by that is if you have lots of parameters in models, like the potential to make very rich models, then essentially they can be very complicated to fit. We'll see that they need lots of data. We've already talked about the curse of dimensionality. So trying to simplify the representation of these models to simpler representations, but still capture the features in the input data is really important. And this is often how unsupervised learning algorithms are used. So again, we're looking for patterns, but we kind of consider two classes of unsupervised learning. On the left here, I can't remember what the data set is, but this is an example of a clustering algorithm, right? So it's trying to group like inputs together so they are treated in a similar way. This clustering, k-means, which we're going to go through in this section as a first unsupervised learning you'll meet, is an example of a clustering algorithm. The top right-hand corner is an example or tries to represent dimension reduction. So dimension reduction is where we have this representation of the full input, which may have many numbers. So for example, a picture has many numbers to describe all the pixels, the colors of the pixels. But do we need all of that information to understand a picture? Is there a much smaller or concise representation in what we call feature space, which allows us to have the same information in our data set, but much more efficient in terms of number of parameters? So examples of this could be autoencoders or principal component analysis, and I'll talk a bit more of that. So this is dimension reduction, that we're trying to find a reduced representation of our parameterized models. Super helpful at the beginning of dealing with data. Okay, so let's quickly cover what we mean by k-means. So as I already said, k-means is a clustering algorithm. I don't know, put a strapline, birds of a feather flock together, right? So the idea is that the means bit says, okay, what we're going to try and do is assign, put the data into k clusters. So here again, we've used k equals 3. And what we're trying to do, the groups to which the data is assigned to, or the classification to which it's assigned to, is chosen so that it minimizes its distance to the mean of that cluster. So if you take the mean of all these points, it sits somewhere in the middle. It's called the centroid. And actually, all of these points so each of these clusters has a centroid. And what you see is actually all these points, the closest centroid to all these points are one cluster, and the same here and the same here. So this is where ring fencing, clustering data together. Nice simple algorithm, pretty easy to implement, can be really useful for sort of deciphering different types of behavior in your dataset or patterns. We'll get onto that more. And then principal component analysis, widely used tool, particularly at the early stages of data analysis. What it's trying to do is trying to find the source of variability in your data. So it's a dimension reduction technique. So in this little sketch, we have one input and another input. And if this was your data set, what we can actually notice that in this direction, there is the most variability. There's the biggest spread of data in this direction. Where in this other direction, there is much less spread. So if we had to reduce the dimension from this 2D representation down to 1, a good representation would be just along this axis, because it includes the most variability. And so we can choose to reduce the dimension. We lose some information, but we do it in an ordered way to retain the most variability in our data set. So it's still as diverse as possible, our data set. So we lose the smallest amount of information. Principal component analysis is a linear way of doing this. There's more complicated ways, autoencoder, for example, which we'll learn about. But this is often used at the early data side to try and filter out noise out of data, or only pick the most relevant features that drive variability in that data set. Really important. Always try it at the beginning of a data analysis pipeline. I nearly always do. Okay, so I've covered supervised learning and unsupervised learning. So what is semi-supervised learning? It sounds like we're making up. Also called weak learning. So one thing that often is the case is sometimes collecting labeled data is really expensive. So you can collect inputs, but actually the process of producing labels for that data is really expensive. So just in one slide, trying to talk about how you can use a combination of the two methods together. So on the left hand side, what we have here is only labeled data. So I've got 2 data points, and I want to build a supervised classification algorithm. So I want to classify them as either green or blue for any general input in this space. Well, the best we can do here is the decision boundary is the one that bisects these 2 points. Everything to the left here would be classified as green. Everything to the right would be classified as blue. And that's the best you can do, because that's the only labeled data you've got. But then suppose we have other data which isn't labeled. So these are other inputs. And so how do you use those? Well, if we use a clustering algorithm, that for some reason these points can be clustered and identified as blue, and these points can be clustered and identified as like the green one, then this gives us our 2 labels, right? And I think it's a really interesting point. And then if we can do that, then we can use this clustering and labeled data together to give us a more complicated decision boundary, which is hopefully more accurate than just using only the labeled data itself. So it's really about trying to exploit everything that you've got from labeled data and unlabeled data together in a problem to try and build better models. Right? We won't touch too much on this in this course, but something really important to know about. There's a whole set and class of semi-supervised super learning algorithms. I've touched on it at a very high level. The nuances of this can be a bit more involved, but good to know that, if you have limited labeled data and it's hard to collect more, then this is something that you can look up and use, right? So reinforcement learning, I call it learning from experience. It's really about how do you learn how to control systems, and I love it as a topic. I think it's a really exciting area of machine learning. I think there's been growth in it. There's lots of open questions, but more and more we're seeing it used. So I'm going to go back over my favourite example. You've seen this before, but just to recap, what we've got here is a 2-legged giraffe, is the best I can describe it. What the algorithm can do is it can control how the muscles contract, and this causes this 2-legged giraffe to walk, fall over, or completely lie down, you'll see. And the question is, can a machine learning algorithm learn how to coordinate those muscles together to walk forward and also remain upright? Right, so you incentivize it. Its objective, its reward is essentially to remain upright and walk forward. And the algorithm, so I'm going to run this now, after different generations of this algorithm, it's gradually learning better and better and more stable control. You see in the last one that, by generation 900 of this algorithm, it's learned to walk off into the sunset. Really nice example, quite fun, but an example like how we learn from experience of trying different things about what we call a policy on how we decide to control this system, how we get it to walk towards, literally in this case, something with a good outcome which we define. So in more general case, we think of reinforcement learning, there's this sort of intricate pairing. So we talk about an agent. So the agent in the last case was the giraffe, right? It's learning how to act within its environment, and that's the thing you're seeking to control. So this agent interacts with an environment. This environment can be uncertain. It doesn't have to give back the same things. Often it can depend on other agents as well, or what these are called multi-agent systems. Really interesting problems. But then just to go through some terminology in reinforcement learning, we have state, which is a representation of that system in a snapshot of time. Action is the range of possible options available in terms of actions it can take at a given time. And then reward is a feedback mechanism to say how well it's done, essentially, once it's chosen an action. And this reward is fundamental to how you incentivize it or reinforce it to do the behavior that you want. Think of it like training a dog. So just to say, in this example, Pac-Man is like a classic example where people test out reinforcement learning algorithms because it's fun, right? And it's, complicated to an extent. So here, the state representation is probably the representation of the system, the location of the ghosts, the direction they're traveling in, because you can't tell if this one's going up or down, so direction as well. The number of counters that remain and where the big counters are would represent the state of that system. The action, so at any given step that a player can choose to go up, down, left or right. And so they're the actions available at any given step. And then the reward is defined by the game. So I think with this, I can't remember, I haven't played Pac-Man in a while, but essentially you get 5 points, is it, for eating these small ones, more for the big ones, but that then changes these into friendlies that you can eat once you go past the big ones. And then if you eat a ghost, you get a certain number of points. And then ultimately you complete the game by eating all of these crumbs, shall we say. Obviously, if a ghost catches you, you lose, and that results in a negative reward, or it terminates the game, actually. And your overall score is you're trying to maximize this, you're trying to collect all the crumbs. So every time you go through a step of this, the state gets updated. The agent has the ability to make an action, including the null action, no actions taken. The environment increments, it then says, okay, now based on the actions you've taken the state, it passes back a reward and the state gets updated, and we repeat this continuously. So fundamentally in reinforcement learning, there are two broad classes of methods. And then, of course, it's not that simple because there are combinations and hybrids of the two. But generally, we can think of value-based methods. And so in this case, we choose to take actions in this system which maximize the value. So at a given state at time t, then say that here we have 4 actions that we can possibly take. We get a new state and we have a value associated with taking that action to the state that we're in. So basically we can think of this as taking a state and an action as an input. So given a state, if I take an action, what's the value of that action given my state? This then becomes a regression task, actually. These are inputs and the output of the machine is a value, a number. Basically, a value is the estimated of all future possible rewards, discounted, but we won't get into that now. But that's, and so the value state basically says, okay, what's the value in my state? If I take this action, I will then choose the action which leads to the highest value position, or the likely highest value position. So just to talk about a classic example with noughts and crosses, what we have here is towards the end of a game, we're going to pretend that we're putting down crosses. So we've started, we put a cross in the middle. This is our state. So this representation, 3 crosses, 3 zeros. And then we have 3 possibilities of actions we can take. We can put an X here, bottom right, bottom left. So the idea here is if we put it in the top right, then there are two possible outcomes that can. Either the zeros are put in the bottom right and then we complete the diagonal, or they put it rightly so in the bottom left and then they can't complete the diagonal and it's a zero. So in this case, it's a draw. So we give it 0 reward. In the case where we win, we give it 1. If it was in a losing position, we could give it -1, for example. We repeat this process. So if you put it in the bottom right-hand corner, actually both the possible outcomes come here as to be a draw. So there's 0 reward in this case. In the opposite case, it's almost the same as the first case, just slightly differently. There's one possible win outcome and there's one possible draw outcome. So under the assumption, that there's no discounting, we won't get into that, and our player plays at random, then we can essentially assign the value of each of these positions as the average of these two rewards. So the value of this action is essentially a half of 0 plus 1. This one is 0, the value of this position, the value of this is a half. So actually, the best move I can take in this situation, given what I know, is either A or C, which makes sense, right? And I can't really choose between the two of them. I'm indifferent. I think of another area, so we've talked about value-based methods, so making decisions to maximize the value. Of course, it gets a lot more complicated than this. There are lots of actions you can take. There could be all sorts of, almost an infinity of combinations that could result. Think of chess, for example, much more complicated game than noughts and crosses, but the principles could be the same, right? In policy-based methods, the approach is different. In this case, we are trying to learn, given a state, what action should we take? And we learn, it's called a machine-learned policy. This is a policy, a mapping from state to action in a system. And then we try and learn this machine to maximize the reward. So we reinforce policies that lead to good rewards. This obviously involves kind of supervised learning algorithms. The object is, instead of minimizing the loss, so the fit, we're maximizing a reward, but in essence the same. These are often very common. They're often used in combination with value-based methods. They're widely used in lots of exciting different areas. Okay, so this was a flyby tour of supervised learning primarily and unsupervised learning. We then touched on semi-supervised learning and then my favorite, reinforcement learning associated with optimal control. Takeaway messages from this and things we're going to focus on: know the difference between what a supervised learning task is and what an unsupervised learning task. Understand when you might use them. Start building up your toolbox of methods that you know about, which you can use in each case. What are the benefits, pros and cons? In this in this course, next section, and the remainder of the course, and the wider AI in the World course, you will have lots of examples of, I would say, dominantly supervised learning algorithms, but some really important and useful unsupervised learning algorithms. So this is the start of your journey there. Great.